Because we need fewer joules to heat up copper to the same temperature if we have the same mass, then to get less joules out of a fuel, every joule, remember the units we used to use before, how many megajoules per mole of fuel? And so we would need less moles of fuel to get less joules. Correct. All right, so then what if we then poured cold water into those pans that were all finally heated up to 100 degrees Celsius? So the second question that I have tries to get at, if we had all those 4 pans that were all the same mass and we'd heated them all up to 100 degrees Celsius, which one of them would cool down the quickest if we turned off the heat, added cold water? Which one is going to cool down the quickest with room temperature water in it? Not much beyond a 1-to-1 ratio. I'd like to hear from a couple different people. What are your guys' thoughts on our logic behind determining which one would cool down the quickest or the most, would go down to the coldest temperature? Kyle?
Okay, our group chose B. I was thinking that because it took the least amount of energy to heat up, it would also take the least amount of energy to cool down. That was the logic I had.
Okay. Does anyone want to add to that as well? Gail?
Well, if copper is the best heat conductor, that means it can go either way. So I would think that's the easiest one to cool down.
Yeah, so kind of building off what Kyle said, that the amount of heat required to raise the temperature is relatively low. The amount of energy required to warm it up, and hence the amount of energy released when it cools down is also going to be low. And so I think one of the big things that I want us to think about here, you've already had 2 today. You've already had 2 today, so go ahead and hold on to it unless it's something that I totally missed and we need to hear, okay? So one way to think about it is if we did heat all of them up to 100 degrees Celsius, the amount of heat required to warm up this one is going to be very little. You can almost think of that as the total energy of that system is much less. So it doesn't have as many joules to transfer back to the water. So it's going to the water is going to pull those joules out relatively easily because there's not as much heat to pull out of that metal. What do you guys think about that? So if we heated up aluminum, a block of aluminum that weighed that much, it's going to have a ton of joules that were pumped into it. So if we add water to it, that water, in order for that water to pull the heat out of the aluminum, is going to have to pull a lot more heat to get the temperature to go down. Building off of exactly what you guys said. So whenever we're doing questions regarding specific heat, it's really important just to think about the units, and then those units can kind of drive our understanding of where heat is coming from and going to. What questions do you guys have on this? In your lab, how did we use specific heat? Talk to your neighbor for a second. Try to remember back in our lab where we did thermo, we had the coffee cup calorimeter. How do we use specific heat? What was that useful for? Does this look familiar? Okay, so I think you guys have a lab final this week, and it includes this, so it's going to be worth going back and studying this. So what happened in the lab? Can someone describe in 15 seconds what we did in the lab? The coffee cup calorimeter lab. You volunteering, Eric? Go.
We were determining the heat given off by a reaction.
Great, simple enough, that's it. We did a chemical reaction, we added a strong base and a strong acid, right? HCl and NaOH. When they combine, how much heat is released or absorbed? That was the question we asked. Did we measure the temperature of the HCl and the NaOH?
Yes.
No.
No.
What did we measure the temperature of? Water. We measured the temperature of the surroundings, the heat that was given off by the chemical reaction. The bonds were broken and formed. Overall, that was an exothermic reaction, so we measured the change in temperature of the surrounding water. That was what we measured, was the change in temperature. And so the question is, well, that change in temperature doesn't tell us energy, right? What if it had been steel that was absorbing the energy around it instead of water? How would that change our calculations? What if the reaction had been done in another substance, another surroundings? What would have changed about this equation? This is our specific heat. Right, so if we're measuring how much the temperature of the water goes up, we really don't care about the temperature change of the water. We care about how many joules of energy were absorbed by the water. And remember, the units of this are how many joules to raise every 1 degree Celsius for every gram. If we measure the change in temperature as 16 degrees Celsius, we know how much the water weighed. We can figure out how many joules were transferred. So, right, we have the mass, we have what the change in temperature was, and that specific heat allows us to determine how much energy was transferred. That's what that whole lab was about. Once we figure out the energy that was absorbed by the water, how does that relate to the energy that was given off by the chemical reaction? If I could spell. How's that related to the system that we were studying, that chemical reaction, the HCl plus NaOH? Are they the same as each other? One's negative, one's positive. However much heat is given off by the chemical reaction is the same as the heat that's absorbed by the water. That's where that change in temperature comes from, is the heat being given off by the chemical reaction, which is absorbed by the water. Other way to say it is, if you add them together, the universe does not gain or lose energy. It's transferred from one to the other. Okay? So let's build off of that. This is something that you're required to do in the American Chemical Society test. So Joey, to your question, is there going to be homework? Yes. There's going to be at least some questions that I put up there that have you work through specific heat and using specific heat, because I want you to be prepared to crush that exam. We're also going to finish what we were talking about last class before Thanksgiving, talking about, can we figure out how far you can travel using a certain amount of fuel? And then we're going to take some of the concepts we learned throughout the semester, determining the identity of an unknown substance through combustion analysis. You guys love those questions, right? It is a cumulative exam that I'm giving you and that the ACS is, so you need to be very comfortable in doing that. And then we're going to be talking about molecular shape. Throughout the week, we're going to be going back and talking about isotopes, and we're going to be talking about a number of the concepts we've worked on throughout this semester. All right, can I get a volunteer to read, or do you want a question first?
We ought to bring a note card for the.
Not for the ACS final, no. No note card allowed for the ACS final.
What about your final?
Yes, I'm 90% sure that the answer is yes.
How many note cards do you
Gail, can you send me an email with the note card question about my final exam, please? And then I'll remember to, not how many.
Will they give us formulas, like any formulas?
There will be no formulas, no. Go back and look over the test. I don't know that you need the formulas you think you need. I would argue that you guys will be pretty strong without it. Can I get a volunteer to read out loud? Kayla, go for it.
You are a part of a team that is planning an expedition to the North Pole to quantify the extent of polar ice caps melting, which is a direct measurement of global climate change.
You want to keep going?
Your expedition will use biodiesel in order to minimize contributions to further global climate change.
Seemed kind of silly to drive a vehicle with gasoline up to the polar ice caps. You want to finish?
You order 250 liters of methyl oleate, one of the major components of biodiesel, which you will use to power your motor vehicle.
And just to remind us all, formula methyl oleate, balanced equation for the combustion of methyl oleate. And do you guys remember how much energy is released per mole of this reaction?
1 negative 9.81
9 is it 81? 1.8 megajoules of energy is released for every 1 mole of that fuel burn.
What is that number again?
I think it comes up again on the next slide. All right, so the change in enthalpy of the reaction is shown in the top right. These are some of the conversion factors that you might need. I want you to determine how far this vehicle can drive with 250 liters of this biofuel. Please raise your hand if you'd like a little assistance in getting started.
Yeah. So you have to go from liters to grams, and then from grams to moles, and how much energy releases, and after that to...
Sounds like you're on the right process. Go ahead and write it down. Think through it. Talk through it. If you're starting by doing a whole bunch of little calculations, what are you hearing me say? Dimensional analysis, please. Please try to combine as many steps into one calculation as you can.
A lot, not very much.
Where are you going? Like, what do you want your engine to do? Where are you?
Yeah, so that's one of my, how do you get to see?
You guys need every single conversion factor that you have, so be careful which ones you use. You're not going to find it there. That's what we covered in the last class.
That's for water. That's for I think it's coming up there.
So there is, not intentionally, but there is a little bit of a think before you write built into this question. Did you guys notice what it is? One of the first couple steps. So the density on your paper is the density of water. Is that any good in this question? Okay, so be very careful to read all the details. After going through a lot of your exam wrappers, a lot of you said, I wish I read the question a little more carefully. So this is kind of an example of that. It wasn't intentional, but it can be a place to really make sure you're specific.
Yeah, so Cam, like you're getting what
And for those of you who already submitted your answer, think about sig figs.
Yeah, I did that. I saw that. I was like, oh, yeah, great. Because I did all of this. Yeah. No. Because you know what that negative just But first we have to figure out how much energy it takes to bring it up. My friends like brought me and like sat there and was like gonna make
I'm only doing undergrad. Okay. How many degrees? Great. Not even 25.
I don't want to go to I think my go talk to her. I need to sleep. Oh yeah, we did really well. It was impressive. Like, I don't know, I swam as fast as my other guys swam like at the end of the season. Like you swim the swimming against like we're supposed to we actually stayed. I don't know, but you said it like it wasn't. I knew you were
All right, I hear a pretty good increase in the noise level in the class, which tells me that you guys, most people have gotten a chance to write it out and find a value. So, going way back to the beginning of the semester, we're thinking about dimensional analysis, unit conversion. First thing that we do is, can I get different volunteers to shout out different parts, raising their hands, please? I want to hear from different people. How do we always start a dimensional analysis problem once we recognize it is that kind of a problem? Christina?
Start out with the number they gave you.
Great. We identify the numbers they gave us, and then what do we do with that?
I put it 1 liter over 1,000 milliliters.
Wait, not the calculations we do. So we identify, maybe, can someone reiterate what that first step is? Looking at the problem, identifying, what do we identify from the problem?
How far you can drive.
So the beginning and ending units, I think, is a combination of what everyone said. So we know that our starting value is 250 liters of methyl oleate. And our final unit, what's our final unit going to be in the end? Miles. Okay? So that's the very first thing we always do. We set up our bookends. We decide, okay, this is what unit I start with. This is what unit I'm going to need to get to. All right, and then can I hear from another person our first conversion factor that you might use, Sarah?
Convert it to milliliters, so we would do 1 liter on the bottom, and then 1,000 milliliters on top.
Okay, and if you want, you can specify methyl oleate, so it converts nicely. Okay, what would we do now that we know how many milliliters of methyl oleate we start with? Matt?
You would do the density of methyl oleate, so do 0.874 grams over 1 milliliter.
And I would once again specify methyl oleate. Why would I specify methyl oleate here? So we don't use the density of water? Okay, that would be good. All right. And then we say that is 1 milliliter of methyl oleate weighs that much. So can you say in a sentence what this is converting from to the type of units, Matt?
Is it from volume to mass?
Great. Volume in milliliters to mass in grams. Okay, now that we know how much it weighs, the 250 liters weighs in grams, what do we do next, Jason?
Figure out how many moles we have.
How do you figure out how many moles?
You put 1 mole on top, and then the molecular weight, 296.478 grams on bottom.
Dad brain, it's all good. All right, so now we know in our 250 liters of methyl oleate how many moles of molecules are there. Why is that useful? What can we do next? Amber?
We can find how much energy by using
How much energy?
the release.
Great. How much energy is released when we burn 250 liters of methyl oleate? What do we use for that?
Use that number you have up there at the top, so you can put 1 mole on the bottom, and you wouldn't want to have it as negative.
Yeah, negative doesn't really make sense here. It's the amount of energy. And so we'll see in a second how we use energy as a whole. So 9.181 times 10 to the, what is mega? Okay, what is mega? Is mega bigger than kilo? Yes. Remember we had 1,000 kilojoules, so we call that a megajoule. So it's 10 to the 6 joules.
You don't need to convert it to joules, because it's the next thing we use is
Okay, so yes, if we wanted to, because we have mega in one of our conversion factors, we could leave it as megajoules if we wanted. All right. So then, Avery, do you want to take us to the next step?
Sure. So then I go multiply by 1 mile on the top, and then on the bottom be 2.514 megajoules.
Okay, so what I'm hoping you guys are starting to do is when you see times 10 to the 6, you know that's mega. So you could say times divided by 2.514 megajoules. That is a completely accurate statement because that 10 to the 6 just stands for mega. Mega stands for that. Okay, so if we stop right now, what units do we have? Miles. All right. And one of the things you'll notice that I do intentionally is I give you extra conversion factors that you don't need. You need to be able to sort through information and select what it is you need. So for instance, one of the things that I do like is, Gail, can you hold up that piece of paper right there? I do like giving you, let's see if you can see it, a table like this where you have to go find the appropriate information and use it. You will have to do something like that in my final exam. There's a much, much, much smaller one in the American Chemical Society exam, so you need to know how to look through that, find a particular compound, and use that delta H. Kayla?
On your exam, will the table be for formation or the AC? Because like on Singa's, most of the questions were for formation, and that package you gave us wasn't formation.
Correct. So whatever table I give you on the exam, you will use values from that and only that. You're not going to use ones, oh, I remember for this it was this value. As long as you stick with one table for every single calculation, for every reactant and every product, you will never have a problem. So whether it's formation or atomic combination.
On your final exam, is there going to be like an equal percentage of questions from each, like from the first?
There will be a tiny bit more questions from everything post-exam 3 because you haven't been tested on that yet. So that will probably be, I don't know, 40, that's not true, 30% of the exam, 35% of the exam, and then the rest of the semester. A lot of the things from the earlier parts of the semester feed into this, so just know that the stuff you haven't been tested on, it's going to be there. Redox, gas laws, thermo. All right, can someone give me a value that you calculated here, and then we'll figure out what to do with that number? Can I have a hand raise? Go ahead, Angel.
2,691 plus 3. Oh, and then put it into sig figs.
But before we do that, what's the unit?
Miles.
All right, and then the question becomes sig figs. How many sig figs should we have? Hold up your fingers. 1, 2, 3, 4, 5. I see mostly 3s. Where does that 3 come from? Because the 250 has a decimal point there, that specifies that that 0 is a certain 0. We know it's exactly 250 liters to the ones place. So that's 3 sig figs. So then how do we type in our answer if we're submitting that? Angel?
0.69 times 10 to the third miles.
Great. That's 3 sig figs. That is the appropriate answer. So then the question is, does this make sense? We have, can you picture 250 liters? How many gallons is that? I'm sure someone calculated that, right?
65.
How many?
65.
65. So a regular pickup truck has a 20-gallon liter, right? This is about 3 times, so you fill up your truck 3 times. Do you think we're going to be able to drive across the country? 2,700 miles in a vehicle that's this giant Arctic Explorer?
No.
Okay, so pause. So the question then becomes, talk to your neighbor. What are we missing? Something's very wrong with those calculations. Go ahead and talk to your neighbor. What are we missing?
Oh, yeah, that's right. There's nothing. Yeah, burn fuel doesn't have, 1%.
Okay, so I saw Amber raising her hand before we even discussed. What were you thinking?
I was thinking gas mileage, how efficient is the engine that's burning?
Well, so that's this, in a way, right? That's how many joules are required to drive 1 mile. And there's something kind of related to that. Okay, so that might not be true for the average, but still, driving across country on 3 tanks of gas seems outrageous, right? Matt?
Because only about 20% of the total input of energy is work, the other 80% is lost as heat. So it's really only about a fifth.
So in particular, we're thinking about the total energy lost. That's what we calculated, right? Using that value, that's how much energy is released. It doesn't say if it's heat or work. So it's a combination of heat and work. We know that very little of that goes towards work. And so for a vehicle this size, it's probably going to be about 15% efficiency. So now I want you guys to calculate how far we can actually get with 15% efficiency. So go ahead and click in your answer.
So, he says that there, but like, he doesn't say that in the problem, but like, if you buy a car and it says you get 20 miles an hour, it's not going to say you got to calculate it. I mean, so if you're calculating that with shouldn't be a speed that the car can actually travel 2,391 miles?
So this right here is specifically work. This doesn't take into consideration the heat cube.
But it said that it requires that much work to drive 1 mile, and you're getting that work from burn the fuel.
That's how much work it requires to go 1 mile, not how much heat is also released. So that only considers the work component of it.
I would imagine that if you were going to try to observe and get data on the effects of a sea ice melting, would you like be on the ocean in a ship?
You could do that, or you could go to one of the places where the ice. You can take a ship to the edge of the ice and then drive it to the center of the ice. I don't know,
Yeah,
lots of things. This is not the most well thought out question ever.
Ship, and
I'm on a boat.
And the boats that, you know, their fuel efficiency is normally around 20, 25, maybe 30%. You know, so it's not going to be 15%.
So are we going to be able to go more or less miles now that we're considering that we're actually losing a lot of that energy transfer in the form of heat? We're going to be able to go less. How much less? I think using math terminology, about a fifth of the distance, right? And so how would we calculate that? Can I hear from a new voice? How would we calculate the actual distance we can travel? Ruby? What was it? 2692. 2691.43 times 15%. What did you find? 403.715, you said? Alright, that might be a bit more troubling. And then with that distance, how do we do sig figs for this? We know this one, if we reported it out, was 3 sig figs because it was limited by 250 liters. How many sig figs is 15%? Is that very accurate?
No, it's not.
It's about, right? Because there's hills, because there's valleys, all these different things. So this is 2 sig figs. So our final answer?
Beef being 2 sig figs, so
4.0
times 10 to the 2 miles.
If it's someone's fuel efficiency, do you think that's a really precise number that doesn't vary? That we could go look up a much more precise version if we wanted to? That's how I want you to think about sig figs. If someone went out and measured it and it has some uncertainty and they only report it in so much certainty, then that's what we need to use to limit our final knowledge of the correct answer. All right. So, how do you guys feel about combustion analysis?
You'll find out in a week.
All right, so let's do this. For class on Wednesday, would you guys all do this as your pre-class quiz? Or should I do something on OWL to make sure you guys do it? Raise your hand if you are willing, if you are committed to doing this question before you come to class. Raise your hand if you'd rather have OWL, because it forces you. All right, so we have 4 to 1. So those 4 people who didn't raise their hands, everyone, please complete this question. It is on your worksheet. What question number is this? 5. Question number 5 must be completed when you arrive in class on Wednesday. There will be no pre-class quiz. There will be one for Friday, though.
When you calculate the grams of carbon, it's more than the grams of fuel total. It was like 1.68 over here, and the gram total was 1. So, I don't know, I couldn't script the calculation.
Maybe I need to go look at that right away.
I think I know pretty much what I need to learn. It's going to be like straight
That was good. All right, I need to correct that. Calculations of my alphas, I guess.